Hey everyone, and welcome to this explainer. Today, we're diving into something that's totally invisible, yet absolutely crucial to the everyday modern technology you and I rely on. We're talking about the Hall effect, and specifically, how a magnetic field reveals hidden charges. You know, we often take for granted how things work. We just see the sleek surface of our gadgets and machines, but beneath that surface, right down at the atomic level, there is this constant, invisible dance of physics happening. And our goal today, we're going to map out one of the absolute most fascinating examples of this unseen world.
So it really begs the question, doesn't it? How can a simple magnet reveal the hidden electrical charges powering our world? We're going to move from this abstract, unseen physics stuff straight into some truly tangible engineering marvels. By the end of this, you're going to understand exactly how engineers use a fundamental law of nature to sense everything from the speed of a car wheel to the exact orientation of your smartphone, all without ever physically touching the moving parts. Pretty cool, right?
Okay, let's dive into this. Here is our roadmap for today. Number 1, moving charges and magnetic fields. Number 2, the Lorentz force push. 3, balancing act, finding equilibrium. And finally, number 4, real-world Hall effect applications.
Let's start with Section 1, moving charges and magnetic fields, the foundation.
All right, let's look at the baseline setup. Step 1 is super simple. Just pass an electric current through a conductor. When we do this, we're essentially creating a microscopic river. The electrons begin flowing continuously in one single direction. It's orderly, it's highly predictable. But then, in step 2, we introduce a bit of conflict. We take that conductor and place it into a magnetic field that is exactly perpendicular to our flow of current. Imagine you're just walking down the street in a straight line and suddenly, wham, a massive crosswind hits you right from the side. That is exactly what our electrons are about to experience.
Which brings us to Section 2, the Lorentz force push, magnetic crosswind.
Let's define exactly what this so-called crosswind actually is. In physics, it's known as the Lorentz force. The equation here is F equals qvb. Basically, what this states is that the magnetic force, that's the F, acting on a particle is equal to the particle's charge, q, multiplied by its velocity, v, multiplied by the strength of the magnetic field, b. Because these electrons are moving straight through the magnetic field, they can't just flow straight anymore. They experience a literal, physical deflection. The magnetic field is physically pushing these moving charges toward one specific side of the conductor.
Now, what's really interesting here is visualizing this whole tug-of-war in action. Take a look at that flat golden plate acting as our conductor. See the brown arrows labeled I? That represents our electric current flowing horizontally just straight through the plate from left to right. Now look at the red arrows labeled B, pointing straight up. That right there is our perpendicular magnetic field. Now, because of that Lorentz force we just explored, the electrons, which, remember, carry a negative charge, are being physically shoved toward the front edge of the plate. You can see them crowding there, marked with the minus signs. And because all those negative charges are abandoning ship and crowding one side, it naturally leaves a net positive charge on the opposite side, marked with the plus signs. This separation of charge literally creates a measurable voltage difference across the width of the plate. You see that meter connected to the two sides? It's actively reading that voltage. That reading is the Hall effect in action. We are using a magnet to push hidden charges to the edges where we can actually finally measure them. But you know, these electrons don't just keep piling up on one side forever.
So, how does it stabilize? Let's look at Section 3, balancing act, finding equilibrium.
So as those negative charges pile up, they start pushing back. This fight back creates an electric field. And eventually, the electric force perfectly, exactly equals the magnetic force. We represent this as QE equaling QVB. Now, if you just cancel out the charge Q on both sides of the equation, you are left with E equals VB. This right here is the precise moment of equilibrium. The push of the magnet is perfectly balanced by the repulsion of those crowded electrons. And it's this exact state of equilibrium that ultimately stabilizes and determines the final Hall voltage that we measure on our meter.
Now, if you're studying physics, you might recognize that this stretches a bit beyond the standard high school textbooks covering basic moving charges, magnetism, and current electricity. But as this quote highlights, although the Hall effect isn't covered in deep detail in curriculums like NCRET, it is a brilliant synthesis of all those fundamental concepts. Really grasping this equilibrium is absolutely critical for JE Advanced, for engineering, for higher level studies. It's the bridge. It's the bridge between pure textbook theory and actual applied technology that gives our machines real-world superpowers.
Let's move to our final stop and see how this builds into those superpowers. Section 4, real-world Hall effect applications.
Because the Hall voltage changes instantly based on the strength of the magnetic field, we can use it as a highly precise, contactless sensor. And the scale of this? It's massive.
Hall effect sensors are what tell your car's anti-lock braking system exactly how fast the wheels are turning. They power motorcycle speedometers. You know when you open your smartphone flip cover and the screen just magically turns on? Or when you use the digital compass to find your way? That's a Hall sensor. They regulate computer cooling fans, they control the precise timing in brushless DC motors, and they act as absolutely critical position and speed sensors in massive industrial automation systems. The Hall effect is literally everywhere.
And this brilliantly illustrates how it actually comes together in real life. In this schematic of an ABS wheel speed sensor, look right there in the sensor head, you'll spot the Hall element. That's the tiny semiconductor plate we've been talking about this whole time. Just below it, across a really tiny space called the air gap, sits a magnetic encoder ring which is attached to the rotating part of the wheel hub. Now notice this ring has alternating magnetic poles, so as the car wheel spins, that magnetic ring spins too. The magnetic field passing through our fixed Hall element constantly fluctuates up and down, causing the voltage in the sensor to spike and drop in response. The car's computer just counts these voltage pulses to know exactly how fast the wheel is rotating, and it does it without the sensor ever once having to touch the spinning wheel. It is a purely magnetic interaction, utilizing everything we just learned about the Lorentz force and electrical equilibrium.
So the next time you have to brake safely in the pouring rain, or you check the compass on your phone to see which way is north, remember that tiny invisible dance of electrons and magnetic fields making it all possible. Which leaves us with this final thought to chew on. If a simple magnetic field can reveal hidden charges in a wire to power so much of our modern world, what other invisible forces are shaping the technology you use every single day? Keep questioning, keep exploring, and hey, thank you so much for joining me for this explainer.